And our next speaker is Jonathan Smoker, and he's going to talk to us about a mini survey of time variable structures in the ISM. So hopefully telling us how we can all use LSST.
Hello. Oops. No, that's not. I'll just hold it like this. Okay, is this a pointer? Yeah. Oops, going backwards. Okay, so I'd like to talk today about some observations that we've taken looking for small and tiny scale structure in the interstellar medium. My collaborators with this were my student PhD student Catherine McEvoy and many others. Okay, so the first slide, I'll discuss a bit about the flames Ferris observations towards the Magellanic Clouds, where we looked for small scale structure by putting about 100 fibers towards O and B type stars in the LMC, and then I'll discuss a little bit about high resolution observations towards say O and B type stars in the Milky Way. I'll skip the next slide, which is why should we study the ISM. I think we probably all know about that one, agree with it. So this slide here tells us two ways with which we can study small and tiny scale structure. The first one is basically we can put maybe 100. We have a high resolution spectrometer, and we have maybe 100 fibers. We put each of the fibers on a star. It's a B-type star, fast rotating, so we can see absorption lines in, for example, calcium, sodium, potassium. The advantage of this is one can observe many stars all at once. The disadvantage is the resolution of these instruments. Flame, for example, on the VLT, we may have a resolution of something like 20,000. The other way we can do, so the way we can get look at for smaller scale structures is we can observe a star, and being very patient people in the interstellar medium, we can wait. We wait for it to move, maybe 5 or 10 years, and then we observe the star again, and we look for time variability in the structure. Obviously, the first method, the fibers, one can use an IFU. The IFU separation, the IFU will be made up of many fibers, and maybe one could observe structures of 1 or 2 arc seconds limited by the seeing. The advantage of the second is that we're using the proper motion of the star, and we can look for milli-arc second movements. So what am I showing here? I'm showing a small scale structure in ISM. I think these are data taken by LaRouche and Meyer, and basically almost everywhere you look, you'll see this small scale structure. If you put 2 stars on the slit, you'll see it in sodium, you'll see it in calcium, and with these, you're probing scales of about 1,000 AU typically, and you always see the structure. For the current observations, we looked at 4 galactic open clusters and 3 galactic open clusters and 4 Magellanic clusters, and we have about 100 stars per field. And the results here are typical of what one sees in this work, which is basically, so we show this is a Milky Way component, and we'll have here an intermediate or high velocity component, and then the LMC or the SMC component. So we see the Milky Way component, typically the variation is something like 10% or something, whereas the intermediate and high velocity cloud component, for example, in this cluster, there's absolutely nothing here visible, and here we're about 10 arc seconds away on the plane of the sky, and we see a variation by a factor approximately 10. This is all done in the calcium 2 line. The second way, when we go to this very small scale structure, we're looking for time variability now. This was first discovered, or one of the first observations was actually in H1 absorption lines by Phil Diamond, and that was done. And they said they saw differences on these scales of about 25 AU. This is in H1 now. This isn't in optical absorption lines. And this was also seen, if you look at H1 absorption in pulsars, you observe the pulsar, you wait a few years, and you see if there's any if there's any change. This is not ubiquitous, but it's quite a common phenomenon. These are now optical time variability from several different sources. And the idea that what we want to do now is we want to see how common this optical absorption time variability is. The whole problem is that obviously that we have these. If you see the time variability in the optical, then that therefore means that you may have you need some sort of overpressure, unless you have, as we've seen many times today, filaments or sheets, or unless these structures themselves are being continually regenerated. So this was one of the seminal papers on this by Heiles, I can't remember, 1987. And I'll go now to describe our actual survey. So what we did, we observed 105 stars, either using UVES, which is a resolution of 80,000, spectral resolution of 80,000, and we have a wavelength coverage centered on 390 in the blue and 580 in the red. And we also had we had about 80 stars we were observing there, and we observed another 20 stars, which using the McDonald, because obviously this is the McDonald mirror with the holes in it. So those stars had a time separation of about 20 years, more or less. Although the numbers are small, it's one of the bigger surveys. I'm not sure if it's the biggest one. And as I said before, the stars we were observing were O and B type stars, and they were basically there's no other selection criteria other than they'll be bright enough. The signal to noise ratios we're getting are about 200, so we can look for variations in the column density of maybe 0.1 dex or something like that. So the vast majority of us 105 sightlines, we see absolutely no change. In the sample, the distance moved is somewhere between 0 AU and 1,000 AU in the 5 to 20 years. And as I said, in the vast majority here, red is one epoch and black is the other epoch. The lines here, basically you see, are basically telluric lines in the NAD. Almost the vast majority, so no change. Some we see changes, but we found later on they were actually badly chosen stars because they're basically Wolf-Rayet stars with winds and things like that. And finally, we see changes in actually 5 sightlines. Now, because of we have 5 sightlines in 105 observations, but obviously each sightline has many components, maybe typically about 5 components. So we maybe have about 5 variations in about 500 components approximately. So you see this star here, we see here both the calcium 2 changes, and also the calcium 1 here, we had nothing, and then, we had a component, and then it completely disappeared some years later. We also see here, this is another possible change, but because these data are very old, you see the baseline is uncertain. And then we see a very small change in here. So most of the changes were of this order, so quite, maybe 0.1 dex or something. One thing that we have to be certain of is that obviously the resolution, the spectral resolution, is the same in the two different epochs, which we tried our best. So the analysis, all we did was something very simple. We used a CA1 to CA2 ratio to get an idea of the electron density. Now, obviously, that is a very dodgy thing because typically the calcium 2 tends to be more spread out, and the calcium 1 looks at the more dense gas. Assuming that would be correct, then you assume that the electrons are produced by carbon, and then you assume a normal abundance, and you can get and you have to assume the size as well, and you get an estimate for the final density. Now the thing is, these numbers we compared the numbers using for the sightlines that showed variations with the sightlines that did not show variations, and there was actually very little difference. So I think this whole methodology is borderline, I guess. Right, so the summary is that we have about 1 or 2% of the components show this time variability. What we did find is that in our sample, we had half the sample which had the distance or the movements of 50 AU or less, and we found no time variability in those. Obviously, that 50 AU is an upper limit because the source that's moving can be anywhere between you and the actual cloud. And the electron densities, as I said, imply derived from the calcium 1 to calcium 2 ratios, imply column densities of a few thousand. But as I've explained, this is quite borderline. One thing that obviously one would like to do is actually use HST measurements, for example, if that had been possible, to actually get an idea using the carbon to measure the actual pressure. Okay, so that's it. Thank you very much. Thanks.
Great questions for Jonathan. Right there in the blue.
Hi. In your variations of column densities, is it due to the central optical depth or to the line width? Did you check that there are changes in the velocity width of the lines?
Yeah, the line widths are, as far as one can tell, the line widths are the same. But the thing is, in the UVES observations, for example, the B value might be 2 kilometers per second. The instrumental B value might be 2 kilometers per second. The actual B value may be 1 or something. So we're getting very close to the resolution. In the McDonald data, that's less of an issue, but we didn't actually find any convincing variation in the McDonald data that had higher resolution.
Because in molecular lines, there are variations that have been detected over the time, and the variations are borne by the velocity width. That's why.
Yeah, okay, thanks.
Jonathan, I mean, previously there were quite frequent observations of variability at optical wavelengths. So I was wondering, so you don't have any sources, any common sources, and I'm just wondering, do you have any explanation of why previously people saw large variability and now not much?
In this sample, we had one, I think it's alpha rho, that did have, and we found it ourselves as well. That was the only one I think that we had in comparison with other work, but that was certainly just, we observed it and someone else observed it as well, or they had already observed it actually.
Okay, any other questions? Okay, let's thank Jonathan again.